So here's a car where we're turning the tires to the right.
Okay.
So I'm turning the tires to the right. So, and then there's a force pushing me off to the left. Which you've experienced, I'm sure, in the car. Like, actually, we're turning right.
Yeah.
So, like, I would think, oh, maybe I'll get pushed into it, but since if I'm not, like, say I don't have my seatbelt on and I go at a fast speed around a circle, the car will want to stay in that circular motion, but I'm gonna get pushed out because of the centrifugal force. So that's one way you can think about centrifugal force. So it's kind of like that equal and opposite thing again, like centripetal force. Like my tires are turned that way, so it's gonna want to complete a circular motion. But then the opposite of that is the centrifugal force, which is gonna want to push me outside of it. Since I don't have my seatbelt on, then I keep on. And then we experience a little bit of that when we turn, and then we start going to the other direction. You know, so that's one reason why you want to lean in. And then also the thing about the G forces, there is a certain amount of G forces that we can take because, you know, our bodies naturally are working under this system, 9.8 meters per second. So then what happens if I'm thrusted, you know, 5 times this acceleration, 10 times, they say 10 times the acceleration of gravity. I believe it's 10 times the acceleration of gravity in 10 minutes is about like an average type of comfort level that you can take until your muscles start atrophying from trying to keep up with the force of gravity and, you know, the rocket. So they have to do human centrifuges in NASA and whatnot. So those are the inertial frame of reference, non-inertial.
So what you were saying just now is like, you were saying like if our body can only take like 10 times the force of gravity, or like faster than gravity?
It's the same. It's the same thing. Where it's like what we just said was that we're going about 2 times the force of gravity. So, you know, if I'm attached to the string, then I'm gonna have to try to pull twice as hard as like normally if I'm just hanging from the string.
Yeah.
So then if it's out and moving around, then I'm gonna have to actually use some muscles. I'm gonna actually have to try to hold on a little bit higher or a little bit harder. So that's one thing that I saw.
So that's like, so when you were saying like if we're moving like 10 times faster than the speed of gravity, so that part's like the centripetal force, and then when you're saying our muscles can only take so much, where our muscles is doing like the centrifugal force, and I guess that's why you said after 10 minutes our muscles start to break down.
Yeah, so what's keeping us right, so if I'm going and I'm trying to, like they say, try not they say like don't move
Mhm.
because your muscles, you're pushing
Mhm.
that amount. Because if I didn't have the seat here to help me stay in
Mhm.
and my seatbelt, and you kind of lift up too, so you like kind of get lifted up, and you're like, it's kind of mimicking that force
Mhm.
that wants to like take you out.
Mhm.
So you're like, because I'm strapped in and the system's moving together, like yes, if I try to move my muscles, it's gonna have to be that amount opposite,
Mhm.
like that centrifugal force.
Yeah.
So yeah, it's mainly like the seat, or as soon as you press on the gas and you get pushed back,
Mhm.
that's like the same. That's that same force. The car is moving that way,
Yeah.
but I'm thrusted this way
Mhm.
because of that force. So yeah, hope that answers your question, right?
Yeah.
Yeah.
Makes sense.
Yeah. So that's a lot of what I saw, and then it adds in friction. Centrifugal force is parallel to. So then we talk about friction. The frictional force supplies the centripetal force and is numerically equal to it. Centripetal force is perpendicular to velocity and causes uniform circular motion. The larger the FC, which FC is the centripetal force. The larger the centripetal force, the smaller the radius of curvature, R, and the sharper the curve. So just like we were saying, if I'm going faster and faster and I have a large centripetal force, that's going to be making me stay in this circle.
Mhm.
The second curve has the same V, but a larger centripetal force produces a smaller radius. So I wonder, smaller radius, I guess it has to be if I have less, my radius is changing. If I have less speed, my radius, I have more speed. I don't know if that's the same. Large centripetal force, small radius. Well, anyway, so then it talks about friction. So then it talks about friction. So then we look at calculate the centripetal force exerted on a 900 kilogram car that negotiates a 500 meter radius curve at 25 meters per second. Assuming an unbaked curve, find the minimum static coefficient of friction between the tires and the road, static friction being the reason that keeps the car from slipping. So what they're talking about slipping is that the speed may be greater than what the traction on your tires is.
Mhm.
That's why you want new tires, good tread. So, and then as I'm turning, it's going to be important because, of course, I can go out, I can slip out. So then we're able to look at the coefficient of friction, the minimum static coefficient of friction between the tires and the road. So my centripetal acceleration is mv squared over r, because F equals ma, and a is v squared over r. So if F equals ma and a is v squared over r, centripetal force equals mv squared over r. So and then we got our mass, 900 kilograms, the v squared, 25 meter per second squared, over the radius, 500 meters. So and then we're left with newtons. A kg meter per second squared. And then this is important, assuming an unbanked curve, because later on we can see on a curved bank. So and then the second part shows the forces acting on the car on an unbanked level ground curve. Friction is to the left, keeping the car from slipping, and because it is the only horizontal force acting on the car, the friction is the centripetal force in this case. We know that the maximum static friction at which the tires roll but do not slip is mu s times n, the static coefficient of friction, and n is the normal force. Normal force equals the car's weight on level ground, so that n equals mg. Thus the centripetal force in this situation is the same as static coefficient of friction times n, which is the static coefficient of friction times mg. It's the same centripetal force. So then we see that we can relate, since centripetal acceleration is mr omega squared, or mv squared over r, we can relate these two together. And then we're looking at solving the static coefficient of friction, v squared over rg, which is right here, v squared over r times g, which is 0.13. So the coefficient of friction found in part B is much smaller than is typically found between tires and roads. The car will still negotiate the curve if the coefficient is greater than 0.13. Because static friction is a responsive force, being able to assume a value less than but no more than mu s n, a higher coefficient would also allow the car to negotiate the curve at a higher speed. But if the coefficient of friction is less, the safe speed would be less than 25 meters per second. Note that mass cancels, implying that in this example it does not matter how heavily loaded the car is to negotiate the turn. Mass cancels because friction is assumed proportional to the normal force, which in turn is proportional to the mass. If the surface of the road were banked, the normal force would be less, as we will discuss below. So we have a normal force, our weight, force of friction, which is the same as the centripetal force, the net force, which is the same as the force of friction. And we just saw that the force of friction is the coefficient of friction times the normal force. So, and then we talked about banked curves. And the banked curve is when you're on a racetrack. Racetracks for bikes as well as cars, for example, often have steeply banked curves. So in an ideally banked curve, the angle is such that you can negotiate the curve at a certain speed without the aid of friction between the tires and the road. So, and then understanding that we have the horizontal, so the centripetal force, same as the normal force, sine, because it's in the horizontal direction, and v squared over r. And then this is the vertical force. We see that the vertical component of the normal force.
You're never getting away from the components.
Yeah,
It always
yeah,
comes back to the components.
yeah. It's very important. Yep, it is very important. When did we talk about components? Two-dimensional kinematics. 'Cause I think components come up chapter 3. No, dynamics. Force and Newton's laws. Yeah, so components are real important because of this right here.
Mm-hmm.
How would I know?
Yeah.
How would I know? Like, how can I quantify, what it is at an angle? It's not just ideal all the time. It's not just flat all the time. We live in a 3D world. So now it's like, oh, okay, so now that my surface is at an angle, the normal force now isn't just straight up and down.
Mm-hmm.
Now it's to the side a little bit. So yeah, you're right. So then the centripetal force in sine of theta, and in the vertical in cosine of theta. Or the other way around, the vertical in yeah, I said it right. In cosine theta equals W. Yep, so that's why that is important. The ideal speed to take a steeply banked tight curve, 100 meter radius curve banked at 65 degrees should be driven if the road is frictionless. So that's talking about Daytona. First note, so we get 10 because for horizontal we had n sine theta equaling centripetal acceleration. F equals ma. And then that's the force, mass times acceleration. And then we have the normal force, sine theta in that same direction. And then the vertical force in cosine theta equals mg. So, and then we're relating the two. Now we can combine the last two equations to eliminate normal force and get an expression for theta. Solving the second equation for normal force equals mg divided by cosine theta, and substituting this into the first yields. So then we get mg sine theta over cosine theta equals mb squared over r. Which sine over cosine is tangent. So tan so then mg tan equals mv squared over r. Since there's an m on both sides, I could bring that g on the other side. So tan theta. So that means taking the inverse tangent gives theta. So now I'm looking at theta, the ideally banked curve with no friction. Inverse tangent v squared over rg. This expression can be understood by considering how theta depends on v and r. A large theta will be obtained for a large velocity and a small radius. That is, roads must be steeply banked for high speeds and sharp curves. Friction helps, but it allows you to take the curve at greater or lower speed than if the curve is frictionless. Note that theta does not depend on the mass of the vehicle. So that's why we get, looking at our velocity. So here, calculate the speed at which a 100-meter radius curve banked at 65 degrees should be driven if the road is frictionless. So we have velocity, and then RG tan theta to the 1/2, which is the same as the square root. So and then velocity equals the square root of this. RG tan theta. Alright, so this is the velocity. This is just about 165 km per hour, consistent with a very steeply banked and rather sharp curve. Tire friction enables a vehicle to take the curve at significantly higher speeds. Calculations similar to those in the preceding examples can be performed for a host of interesting situations in which centripetal force is involved. A number of these are presented in this chapter's problems and exercises. Ask a friend or relative to swing a golf club or a tennis racket. Take appropriate measurements to estimate the centripetal acceleration of the end of the club or racket. You may choose to do this in slow motion. So, and then, similar, I have brought this in to mimic that, it is Halloween time. So, but I was looking at this because I didn't see my golf clubs in that storage room. But anyway, this is kind of like the same thing. You can swing, like, it's the same as swinging a bat. I was really thinking about bringing in a bat or a golf club or something, but I figured this could be fitting. But like we have an angular, it's the same thing. It's an angular acceleration, so, or even a golf club, So you could take that same amount of effort understanding what we just did with our uniform circular motion object right here. So you could take that and I could say, well, what's the speed that a golf club is hit? What's the speed of me going from here? Well, not from there, but from here and then up to here. That's 2 pi, right? It's still going 2 pi. From up here to there. That's a whole circular motion. And then also a baseball bat. If I have to go from here to here, then I know that that's pi. So I'm able to see the speed at which I'm swinging the bat, able to see the speed at which I'm swinging the golf club, and then it also has to do with orbits and it's micro scale all the way to the macro scale. So here's our model. Got the gravity force going in. Gravity is what's keeping this in on a higher how can I put that? So and then it talks about Newton understanding that gravity is one of the main forces that's keeping us in line with our orbit. So and then there's a way to see the force of gravity is keeping me in. And then say I have a greater force of gravity with the sun comes in. Now if it's too much gravity, go in and crash.
Yeah.
But we're at a perfect distance where it's almost a circular. It's very close to being circular, but it's still elliptical. So an ellipse means that it's just slightly elongated. So 1, 2. So it's slightly elongated. So as you can see, this is at the middle. So and then if I go two squares, 1, 2, it's right at that 2. When if I go to the left, 1, 2, it's a little bit further than that one on the left. So that's elliptical. It's an ellipse. So it's not exactly a perfect circle. So there's a time where the Earth moves just a little bit faster, which you'll see with the moon, where well, no, that's not the same, but there's something. I think it's going to talk about it. Yeah, Newton's universal law of gravitation. So then we'll talk about more of that with Newton's law of gravitation, because there's more things that go into it. But it's funny looking at this, and an observer might say, man, this planet or this star or this moon, I'll call it a moon, and it's moving, looks like a flower is being made along the Earth. Like, why is it moving like that? And it's the frame of reference, like, yeah, it's constantly going around and around the Earth. But then if I'm looking at it like this, linearly, like in a 2D projection, then it looks like this cool little flower or something. So yeah, that's something. And then
I wonder if gravity works differently on where we're positioned in the Earth, like its effect on us. Like you versus being like, top to like maybe bottom Antarctica type of thing.
so not so much gravity, because everywhere along the Earth you're gonna want to be pushed toward the center. So you're constantly gonna feel that 9.8 meters per second being pushed down to the center. And then hopefully Thursday we'll be able to look at escape velocity. There's an escape velocity, so the amount of the speed that I can go to escape the gravitational pull with the rocket. So no, I don't think so, but what I can say, what else about gravity? Like this, like they call it fictitious forces, because there's a force at play, like we're spinning, but then because we're spinning, there's a little offset. So that's what this is doing. That spin is offsetting